Hey everyone, so I'm going to do number 10 from the WebAssign homework. I've had quite a few emails about this homework, which is totally normal. It's the tough section, and you can always go to Outreach and the Math Learning Center is still taking appointments for future homeworks and all that stuff for Exam 3. But for this one, I completely understand just because there are so many steps. For most of you, it's really tiny mistakes, and it's just a matter of checking your derivative before you solve for dy dx, and you should be fine on this homework. But this last question, number 10, is pretty tricky. We're prepared for it. It's exactly like the questions that we have in the notes. It's just a new word setup, and I think having 3 different variables is tricky. So I'm going to do number 10. I'm going to use my own numbers that I have made up here, so it might not be the same as yours, but it should guide you in how you should do your own. So my W is 15.19 plus 0.6312, and it's a capital T for this problem, minus 11.32 V to the 0.13 plus 0.3988 T times V to the 0.13. So, super long equation. I'm going to give you a second to write that down. What you'll want to do is just take notes with my numbers, and you can try with your numbers. And again, this is only if you got stuck. I know some of you already done with the homework, which is awesome. But I do want to give a resource for one of these homework problems just because this is a really tough section. And I wish I was in person to teach you. It's just not the way that it is. So, we're going to do our same 2 steps. We're going to try not to be overwhelmed by the fact that this is a really long equation that has so many decimal points, which is not fun. But we're going to do our same 2 steps. We're going to take the derivative, and then we're going to solve for the derivative that we don't know in that. So we're going to take the derivative of everything with respect to time. But before I do, I'm going to do my setup so that I'm a little less overwhelmed than I am just looking at this whole problem. So I'm reading off of WebAssign. It says the wind chill index is used to describe the apparent severity of cold weather combined with the wind. So if you live somewhere it's cold, you probably understand this. I'm from Vermont. The coldest I've gone ice fishing, it was negative 30 degrees out already. That was the actual temperature. And then with the wind chill, it made it feel like it was negative 50 degrees. So having it be super windy on a cold day makes it feel so much worse than it already is. So that's what we're talking about here. We have the apparent temperature, which is W. So W is how it actually feels. It's the apparent temperature. And we kind of know this in the South. It's similar to how the real feel of the temp is compared to the temp with additional humidity. That's kind of how we measure heat. Feels worse when it's more humid. Cold feels worse when it's more windy. So we have our W, which is the apparent temperature. And it's modeled by the equation, which I have written down here, 15.19 plus 0.6312 capital T minus 11.32 V to the 0.13 plus 0.3988 T times V to the 0.13. So a super long equation, and yours is probably a little different because we all have different numbers. This is where T is the actual temp. So T is the actual temp compared to the apparent temp. And that's measured in degrees Celsius. So I'm going to get a T, which is going to be in degrees Celsius. And then when I take the derivative, I'm going to have a dt, a weird one. Capital T is for degrees Celsius, and dt, it hasn't told us yet. But looking at this, the next thing it says is V is the wind speed in kilometers per hour. So it looks like our time is measuring hours. So we get our time, and we get V is the wind speed. So we're going to get a V equals, and it's going to be in kilometers per hour. And then we're going to do dV dt, which is going to be in kilometers per hour each hour. Just looking to fill in these variables and derivatives, and it's easier to do if they have the same units. So that leads me back to W, which wasn't very well explained because we weren't given any units on this. The actual apparent temp must also be in Celsius. We wouldn't switch to Fahrenheit. And then dW dt is going to measure in degrees Celsius per hour. So if we go to fill in these blanks, we have some numbers we're given. So suppose that it is currently negative 15 degrees Celsius. So what it actually is outside right now is negative 15 degrees Celsius. Super cold. So it's already negative 15 degrees Celsius. There's the actual temp. And the wind is blowing at 30 kilometers per hour. So that says 30 kilometers per hour. It's not 30 kilometers per hour each hour. It's not how fast it's increasing. It's what it is right now. So that's going to be my V. V is in 30 kilometers per hour. And these are changing. So the next sentence tells us if the temperature is increasing at a rate of 3 degrees Celsius per hour. So the temperature it is outside is increasing by 3 degrees Celsius per hour. So it should be a positive 3 because it's increasing. And the wind speed is also increasing at a rate of 2 kilometers per hour each hour. And it says at what rate is the apparent temperature changing? So this is kind of confusing. It's hard to guess what the answer is going to be. Our temp is increasing, so it's getting hotter outside, but the wind is also picking up. So what's going to happen to what we actually feel? Is it going to feel hotter because it's getting hotter, or is it going to not feel hotter because it's also getting windier at the same time? So that's what we're trying to figure out. What's happening to the temperature that we feel? What's the apparent temperature? We're not given W, how it feels originally. We might not need that, so I'm not even going to plug in. If I had to plug in, I would plug into the original, what T is and what V is, and see what the original apparent temperature was. So I have my whole setup, and now I'm ready to take the derivative and plug in for what I know and solve for what I don't. So I'm going to take the derivative of 1w with respect to time, so I'm going to get 1 dw dt. We don't even need to write the 1. And the next piece, the derivative of 15.19, that's a constant, so that derivative is 0. And then the derivative of 0.6312t is going to be 0.6312. But I took the derivative of the temperature with respect to time. So I get a dt. The next one, I'm going to bring down the power and subtract one for the new power. It's going to be a lot to plug in, but I don't have my calculator right here, so I'm just going to bring down the power and subtract one for the new power. Feel free if you wanted to plug that in on your calculator and make it one term. So I bring down the 0.13 and subtract 1, which is going to be negative 0.87. And then I need a dv dt because I took the derivative of the wind speed with respect to time. This next part is what's really tricky. I have a product rule here. So I need to take the derivative of the first. So derivative of the first 0.3988t is going to be a positive 0.3988. And that's going to have a dt on it because we took the derivative of temperature with respect to time. I like putting those at the end. I'm going to plug in this original second in front of it. I just think it's easier. So what we did was the derivative of the first. Derivative of 0.3988t is 0.3988 dt times the original second, which is v to the 0.13. And then the second part of the product rule, derivative of the first, original second. The second part I'm going to write down here just for space. I'm going to take the derivative of the second term. I'm going to bring down the 0.13, raise v to the negative 0.84. This is going to get a dv dt. And then out front, derivative of the second, I need to multiply by that original first, 0.3988t. So after that, I just need to plug in all of these numbers into the correct space. So I need to replace everything but dw dt. So I have the 0.6312, and the rate that the temperature is changing, it's increasing by 3. I have 11.32 that I need to subtract off there. Do a little dot there. So minus 11.32 times 0.13, and if you have a graphic calculator, it can handle all this at once, so that's kind of nice. I actually just paused and plugged it on my laptop to see. I know some of you don't have your calculator at home, and plugging it in on my laptop, just in my regular calculator, I got the correct answer, so you should be fine. So we have 11.32 times 0.13, we plug in for V. V right now is 30. That's being raised to the negative 0.87. And then dV dt, how fast it's changing, it's going up by 2. Okay, and my next piece, I'm going to plug in the product rule down here. I have plus 0.3988 times my V is 30 to the 0.13 times dt, the rate that the temperature is changing is a positive 3. And then I have plus 0.13 times V is 30 to the negative 0.84 times 0.3988, and then my current temperature is negative 15. And then that gets multiplied by dV dt, which again is 2. So a whole bunch to plug in. Be super careful, double check it if you're not getting it right in WebAssign. It literally could just be plugging it in again and seeing if you get the same thing. I plugged this all in on my computer to see if it would work, and I got the same answer as a graphing calculator. So if you don't have your graph calculator, you can still just use your calculator application on your computer. I got 3.489, and then it kept going for a long time, and WebAssign just says to round to the second decimal place. So I would say this is 3.49, and it's dW dt, what we solved for. So it's going to be 3.49 degrees Celsius per hour. So that means that even though the temperature was going up by 3 degrees and it was getting windier, it still started to feel warmer. And there's number 10 from WebAssign.